Okay, so this video will talk us through how to calculate frictional force applied to an object. So you've seen this simulation before when we were talking about the introduction to forces. I'm going to start to apply 50 newtons worth of force to this crate, which is on a surface that is frictionful because it's a road, let's say. If I start to increase the applied force in 50 Newton increments, what I'll see is that my applied force is going to be equal but opposite of friction force. Right now we're calling that friction force static friction because that crate is not in motion. If I add another 50 Newton increment of force, I still am experiencing static friction because the crate's still not moving and frictional force is still equal but opposite of the applied force. And if I add another 50 newtons worth of force, you'll see that the crate begins to move. My applied force is 150, but now notice that the frictional force has decreased to 94 newtons. And that's because it takes less frictional force to keep an object in motion than to keep an object stationary with static friction. And so this value has now changed into kinetic friction. And we're going to see what that means in the series of slides on the next screen. So here is the definition of coefficient of friction. Every single surface has a different coefficient of friction because every surface has a different roughness. For instance, asphalt is a lot rougher than waxed floors. So a coefficient of friction is a scalar value that relates the amount of friction applied to an object versus its normal force. So the rougher a surface is, the higher the coefficient of friction, and the more force you have to apply to an object to get it to overcome that friction to get the object to move. We designate the coefficient of friction with the symbol mu, which is the Latin letter M, and it's literally pronounced mu because it looks like an M and a U combined. There are two types of friction, like you just saw in the animation. The first type is static friction. And notice here that static friction is defined as the coefficient of static friction times the normal force. This coefficient of static friction, you are going to have a table that is going to allow you to figure out those values regardless of what two types of surfaces are rubbing together. So also notice with static friction that the frictional force is less than or equal to this product of the coefficient of friction times the normal force. That's because the frictional force can be less than or equal to this value before the object begins to move. So whenever you've got static friction, the value that you use is less than or equals to. The other type of frictional force is kinetic friction. Kinetic friction is defined as the amount of force applied to an object by a surface when the object is in movement. So you have frictional force is now equal to the coefficient of kinetic friction times the normal force. And like you saw in the simulation, that the kinetic friction is going to be less than the static friction because there is a smaller amount of force needed to keep that object in motion and overcome friction once you have a certain applied force. Here's a table of values as promised, showing you different coefficients of friction. You do not need to memorize these values. These values can be found on page 138 of your text, although this is a more complete list. Notice whenever you see this table, you have a static friction column and a kinetic friction column. The static friction column will always be higher than the kinetic friction column because it takes more force to overcome stationary objects not moving rather than an object in motion. So if you see steel on steel here, the steel on steel, when you have steel rubbing up against steel, static friction is 74% of the normal force, whereas kinetic friction is 57% of the normal force. So take a moment, read through this table, and think of examples of these two types of surfaces rubbing together. Here is an example problem like the ones you will be solving in the homework this evening. You push a 25.0 kilogram wooden box across a wooden floor at a constant speed of 1.0 meters per second. How much force do you exert on the box? So notice here that it says constant speed. Constant speed implies that the crate is experiencing a state of inertia and all the forces acting upon that object are going to be balanced. So if I draw a free body diagram of this situation, here's my crate. Here is my wooden floor that the crate is sitting on. I can start to draw my free body diagram, applying some forces to this crate. Here is my normal force. My gravitational force is going to be equal and opposite that of my normal force. Then I'm going to have an applied force, and let's say the crate is going to be moving this direction. Last but not least, I'm going to have a frictional force that will be equal but opposite of the applied force so that all the forces are balanced. So if I can figure out the value of the frictional force, I know that will be equal but opposite of the applied force I need to get the crate moving. Label all of these forces. There's normal force. There's applied force. Here is gravitational force, or the weight of the box. And here's my frictional force. So I know that my normal force is going to be equal but opposite of my gravitational force. So it's going to be 25.0 times 9.8. So I'm going to solve that out to start. 25 times 9.8, and I get 245 newtons. So I know my frictional force is going to be equal to, and I'm going to use the coefficient of kinetic friction due to the fact that I know the crate's in motion. Coefficient of kinetic friction times my normal force. I'm going to look back at my table of coefficient of frictions. I will see here wood on wood, coefficient of kinetic friction is 0.2, and it's going to be 20% of the normal force. So I'm going to say 0.20 times, and then my normal force is 245. So I'm going to multiply those values together, and I'm going to find my answer is 245 times 0.2 is 49.0 newtons. So my frictional force is 49.0 newtons. So my applied force has to be positive 49.0 newtons. And so that's how much force I must apply to this crate in order to get the crate to move. So All the problems on page 139, 1 through 3, pretty much are exactly like this. Do not hesitate to ask any questions. Again, here's the assignment. And I will be around to offer assistance.